Hello everyone. Today we're covering cryptography too. So my name is Ahmed Alkhalawi. I'm a helper in SIGPwny and I'm a math and CS major. We're going to play the OSU Gaming CTF tomorrow. So if you're interested, come to Stevo 2406. Is there pizza? Probably. There'll probably be pizza. Okay, this is the XKCD and the meeting flag. So I guess we'll get to. Ron here is one of the people who made RSA. We'll get to why he was wrong later. Okay, so today we're going to cover asymmetric encryption. Asymmetric encryption means that there's a public key which you share to everyone, and so anyone can see it, and then there's a private key that you shouldn't give anyone, or they can break the encryption. If you have the public key, then you can encrypt any message, and then you can send it to someone, and you send it to the person with the private key, then they can decrypt the message. And so this is as opposed to symmetric encryption, where everyone, so you have two people and they both have the same key, and they can both encrypt and decrypt messages. But so here the advantage is that you don't have to. So for symmetric encryption, you need to have both people get the same key. But if you want to give someone the key, then that can be really difficult. Maybe someone eavesdrops on the initial transaction where you're giving them the key. But here, there's no difficulty. And some examples are RSA, which is what we're going to mostly cover today. There's Diffie-Hellman, which we touched over last time. And there are more examples like elliptic curve cryptography, which I don't know if we're going to cover that. So. Okay, so we'll start with, I guess, a math problem, because cryptography is just math. So you want to calculate 5 to the 5 on 113. So that means we want the remainder of 5 to the 5 after dividing it by 13. We could just calculate it, just calculate 5 to the 5 and reduce it, but that would be like, if you want to put bigger numbers here, then that would get really difficult quickly. And you would have like O(n) multiplications. So instead what we do is, so you square 5 and then reduce it to 117. So 5 squared would be 25. And then that would be 8 117. And then you can just square it again and you get 5 to the 4 117. So that would be 8 squared, which is 64, and then you can reduce it to get 13. And then to get the 5, now we can just multiply 5 to the 4 by 5, and we get that it's 14 117. And this works in O log n multiplications, so it's fairly quick. On the other hand, to get the inverse of this, basically you want to take the fifth root of 15 117. So how can we do that? Pointer. Okay. So for this we use Euler's theorem. What it says is that let phi n be the number of the number of numbers less than n that don't have any factors that don't share any factors with n. So for example, 6 and 3 wouldn't work, but 6 and 5 would work. And so we call that the Chauchat function. And Euler's theorem says that if a and n share no factors, they're coprime, then a to the phi n is always 1 mod n. And this is the basis for RSA. And the reason, okay, I guess we'll go back to our original problem. We want to solve x to the 5 is 14 mod 17. Since 17 is prime, every number less than it won't share any factors with it. So that means that phi 17 is 16, because the numbers will be 1, 2, 3 to 16. And so x to the 16 is 1. Now, we know 5 times 13 mod 16 is 1. And that means that we have k such that 5 times 13 is equal to 16k plus 1, because 5 times 13 minus 1 is 0 mod 16. So that means we can raise x to the 16. So x to the 16 will always be 1. And x to the 16 k plus 1 will be equal to x to the 5 to the 13. We already know x to the 5 is 14. So that means that x will be 14 to the 13. And since we can calculate powers mod n, we can compute that to be 5 mod 17. So this is what happens when you have a prime as the modulus. Phi p is just always p minus 1. But if we instead replace a prime with a number n, and its prime factorization is p to the a times q to the b, and so on, then phi n will always be p minus 1 times q minus 1, and then you're going to also multiply by p to the a minus 1, and so on. And this isn't, like, why is this true? This isn't very difficult to show. You just kind of try to write out all the definitions, and maybe you have to do induction, but it works out. So the important thing is that if n is p times q, then phi n is p minus 1 times q minus 1. And what that means is, if you want to compute phi n, you have to factor n. And you need phi n to solve this equation. So that means that to solve this equation, you have to factor n. But factoring large numbers is something like, it's not an easy problem. It's computationally difficult. So that means, so if you want to solve this equation, if you know the factorization of n, then it's easy. But if you don't know it, it's difficult. So that's I guess the basis for RSA, because you can have the prime factorization be a private key, and n and e is just the public key, and we'll get to exactly how it works later. So yeah, say Bob wants to send a message flag to Alice. Then first he can just turn the message into a number. For example, in Python you can do from Cryptodome you can just do a bytes long n, or bytes long flag, and you'll get a number. And then so Alice can choose her public key. First she'll take an exponent e. Usually you take 2 to the 16 plus 1, just because it's easy to compute since it's the power of 2 plus 1, and it's fine. And then she gets large primes p and q, and she takes n times q, which is p times q, is the public key, and phi n, which is p minus 1 times q minus 1, can be the private key, because this is how you can compute d, which is how you can factor. So you compute, so Alice then computes d with ed is 1 mod phi n, and this is, you can do this with the extended Euclidean algorithm. We won't cover that. So now Bob, he has n and e, so he can compute c, which is the ciphertext. The ciphertext, it will be n to the e mod n, and he can send it to Alice. Then Alice can decrypt the message just by taking c to the d. And if we just write out why this works, it will be c to the d, it will be m to the e to the d. That's going to be m to the e, which is m to the 1 plus something times phi n, since ed minus 1 is divisible by phi n. So that will be m times m to the phi n to the k, which is just m mod n. So Bob can get it, Bob can encrypt it, and Alice can decrypt it, but no one else If anyone else eavesdropped on the message, then they can't decrypt it because they don't know how to factor n. So, yeah, I just covered a lot. So, does anyone have any questions about this? No? Okay. Okay. So there are a lot of attacks on RSA where with at least some information or maybe some misconfiguration in the way you generated the primes or something like that, you can just factor n or get the ciphertext or you can get the plain text directly. And so a lot of these ways rely on GCDs, which is the greatest common divisor. And the greatest common divisor of A and B is just the largest number that divides both A and B. And if we can find T such that P divides T and Q doesn't divide T, then since N is equal to P times Q, the GCD of N and T will be P, because there's nothing else that divides N besides P and Q. So this is useful because we can compute GCDs very quickly with the Euclidean algorithm. It just says this is the version of the extended Euclidean algorithm we just mentioned, but that one's like you record more information. So this is the simpler version, and it essentially says that GCD AB is GCD A minus BB. So you can just subtract B from A. And so you can get this just because if anything divides both A and B, it will also divide A minus, right? So for example, if you want to compute the GCD of 807 and 1443, then you can subtract it, like you'll get this, and then you can keep subtracting. Here we have to subtract, like here we subtract a multiple. We subtract 171 times 4, I think, and we get 171, 123, and we can continue, and in the end we get 3. So this is a lot faster than factoring n directly, but we need to find the T that works here. So one way to do that is just like so in 2012, researchers just collected every RSA puzzle key they could find on the internet, and they just took the GCD of every two. So in theory, if our prime generators were random, then this wouldn't do anything because there are just too many primes for two of them to share one. But in reality, it turns out that 21,000 of them had primes that were also in other keys. So they just were able to factor them and were able to really come to 21,000 messages that they found. And this is where the meeting flag comes from, because the assumption of RSA is that we can generate random primes, and it turns out that this is a lot harder than expected. So there's another way here to generate like a T that works. Basically, if P minus 1 is power smooth, that means that any prime power that divides it has to be less than a constant B. Then we can use this algorithm to factor n for any which is equal to P times Q for any number Q. And so if only one prime is vulnerable to this, then you can factor n. And so how do you know if a prime will be power smooth if you just have a public key? Usually, maybe you can see it from, either you can just test this algorithm, and if it works, then that means that one of the primes was power smooth, or you can look at the prime generation algorithm, and sometimes there are weaknesses that will force something to work with. So if we take M to be the product of the largest prime powers less than B for every prime. For example, if B equals 10, then we'll take 8 because it's the largest power of 2, and then we'll take 9 and 5 and 7. If you take M to be the product of all of them, then P minus 1 will divide M, because we assume that P minus 1 or all of its divisors will be included in that multiplication. So that means A to the M will be, for any number A, we can just choose a random number, and A to the M will have to be A to the K to the P minus 1, which is final. So that will be 1, 1, P. And that means that A to the M minus 1 is divisible by P. So this, if Q isn't power smooth, then this will immediately work. So we can take GCD of A to the M minus 1 and N, and it will have to be P. But if it turns out that Q is also power smooth, then we can just reduce B. And if there's any prime that divides P minus 1 and doesn't divide Q minus 1, you can still get it to work. And again, in 2016, this shouldn't, if we have good prime generators, then we're never going to get P minus 1's power smooth, because the chance is so low. But in 2016, 4% of the keys generated by a smart card, this one, are all susceptible to this attack, and they were able to crack them easily. So now, we can take GCDs of numbers to get their divisors, but we can also take the GCD of any two polynomials, which will, for example, and with that we can get the root of any polynomials. For example, the GCD of x squared minus 2x plus 1 and x squared minus 1, we can factor the first one to get x minus 1 squared, and the second one to get x minus 1 and x plus 1. So their GCD is going to be x minus 1. And we can also apply the Euclidean algorithm, and we'll get x minus 1. And this also, like everything here, also works if we take the polynomial mod n. So if we know, say, x squared plus 5x plus 1 has the root x equals 1, mod 7. So if we take it, the GCD with another polynomial that has the root x equals 1, mod 7, then the GCD will have the same root, and it will probably be x minus 1 mod 7. So x minus 1 or x plus 8 or so on. And so we already know x to the e minus c, where has m as a root, because we chose c is the ciphertext here and m is the plain text. So we got c by raising m to the e. So m to the e minus c is 0, which means that x to the e minus c has m as a root. This is all mod n. So if we find another polynomial that works here, we can get m immediately. So one way to do this is that if you have two messages and you know that that their difference is a fixed number, then we can take x to the e minus c1 and ax plus b to the e minus c2. So if the first message is x, and we know that we send the second message and it's x plus b, for example, then x plus b to the e minus will encrypt to c2. So that means that it will also have m as a root. So we can take the GCDs, and this will always be, and like the GCD will probably just be x minus m, where m is the plain text. So we got the plain text. And this, for example, if we send two messages and we know that the messages always have the time attached to the end, then if we know the difference between the times that they're sent, we can get the difference between what the messages will be. So that allows us to decrypt the message. And the Culver-Smith short by attack makes it so that if you have any two messages, and you know that they're the same, except in the end there's some padding that might be different. If the padding is sufficiently short and E is small, for example, E is 3, this happens a lot in CDS to make computation easier, but you can just decrypt it without knowing the padding. So what every modern system that actually uses RSA does is that they also use a padding, But first of all, the padding will be randomized. And usually they XOR it with the original message instead of just adding it to the end. And what this does is, first of all, it stops a lot of the attacks. Any attack that relies on the the ciphertext being just X to the E won't work because you can XOR everything and that will ruin all of the structure. And it will also stop brute force attacks from just taking messages and like encrypting them and seeing if it's equal to the ciphertext. And that because it's randomized. So, so in every modern system, they're going to use this. In a lot of CTFs, they don't. In some of them, they might. If you want to attack a system like this, you usually are going to have to actually factor n, and that will let you solve it. So the fastest way right now we know to factor large numbers in general is called the number of fields C. The record right now is a 250-digit modulus n. It was factored in 2020. If you have anything less than that, then it can be factored just like essentially by brute forcing it. We also have more variants on the p-1 attack. So if p-1 is smooth, we can factor it. If you have p+1 is smooth, you can also factor it using the William p+1. We also have something called elliptic curve factoring, which basically uses if there's any smooth number near p, which has an 100% chance basically, then you can always factor it. But this is a bit slower, and so it's the fastest algorithm we know for numbers that have at least one small prime factor, whereas the number of field C is the fastest for if P and Q are of similar size, then the number of field C will be the fastest algorithm. We also have the Coppersmith method, and so if P is a prime of B bits, and we know the B over 4 smallest bits of P, or we know the B over 4 highest bits of P, then we can factor n. And this was used in 2017. There was a weakness in the prime generator that was involved in a lot of products, and that let you know the significant, I think, bits of the primes, and that so a consequence was that Estonia had to recall 750,000 national IDs because they were all using that algorithm for verification. We also have Wiener's attack. If D is small, if the private key is small, then we can obtain D without factoring that. This is used to minimize the size of the private key sometimes, but like since this weakness was found, we can't use it anymore. And we also have side channels like timing attacks. Sometimes when you have some bits of when we have some bits of the correct prime or the correct key, then it will take longer to work. So we can just measure the time it takes to encrypt something or like to test the specific key, and that will allow us to factor the prime. So that's it. We have for challenges, we have this website Cryptography. This is a really good website. It covers all of the crypto topics. We really don't have time to cover all of them in the SIGPwny meeting, so we should use this if you want to cover everything else. For example, lattices or maybe elliptic curves. And you can also get points on Pwny CTF if you use it. And I think there are also more challenges being uploaded to Pwny CTF itself. Yeah, so this Friday we have the OSU Gaming CTF. And this Sunday, I think Cameron will talk about Python bills. Yes. So, yeah, that's it.
Yeah, I just want to highlight one thing we talked about here, the crypto hack. We do have on Pony CTF, we have some challenges. But our crypto category is like kind of, we have like the least number of challenges in crypto, but thankfully, I don't know who made crypto hack, but this was gifted to the CTF world. So as you can see on Pony CTF, we have this crypto hack category. If you just click on the first challenge and then click this link, it will bring you to the website. You can make an account and then check out the challenges. So today we're talking mostly about RSA, and you can see they have 29 challenges here just on RSA. So if you're confused by crypto and you're like, I don't know what's going on, I'm bad at math or whatever, you can work your way through the intro challenges and go through everything. And by the time you get to the RSA, you'll be like very ready to do these, and you have a million examples and a million common CTF challenges to get you up to speed. So highly recommend checking that out. And then of course, after you do that or in between, you can come back and do some of the Pony CTF challenges. That's all I want to mention.